Okay, so the final talk of Flower Monthly for November is by a student of the University of Cambridge. Um, we have Horan or Samuel G. He is going to show us Strato FL. So it's more of a piece of sort of academic work in the direction of how do we make Federated better. Really excited to see what he's done, the results, what he's found. And yeah, thank you so much for sharing it with the community today.
Thank you. Thank you very much for the invite. Let me share my screen now. So I'm gonna share. I'm Samuel. I'm from Cambridge. I'm gonna share today my dissertation work for my part two project that I did together with Javier, who is also one of the researcher in the Flower Lab. Um, and the name is StratoFL, Federated Optimization for Heterogeneous Molecular Data. Oh, so here's a bit of the overview for the presentation today. Okay, gonna start off with motivations and aims, and then going through system overview of StratoFL. Next up, I'm gonna introduce a bit about the data sets I use for my project, as well as the what I call featureizers. Next up, I'm gonna talk about the different non-IID taxonomies and the partitioners I came up myself to simulate the realistic non-IID scenarios. After that, I'll introduce different aggregation algorithms I've used, and then at the end, I'll share about the evaluation part as well as the results and the conclusion at the very end. So first off, why federated? Why this work? Why? I think it's mainly because of the non-IE federated learning. Yeah, I think all the audiences they're probably uh, already quite familiar with this because we know federated learning is very important, especially for privacy preserving machine learning. It enables when we have multiple organizations, such as hospitals, as the last project was talking about. We have hospitals, pharmaceutical labs, financial institutions. Federated learning allow them to collaboratively train a model without sharing their raw data, and then each client trains locally, and only the updates are being exchanged. And then I'll say the major issue is that in the real world, the data across different clients are really ID, independently dis identical and independently distributed, meaning they're not. So each institution might collect data from different populations using different experiments or under different experimental conditions. So this could be in my specific context of molecular machine learning, this non-idealness could appear in different forms, such as perhaps some labs specialize in small molecules, others in large compounds. Some assays record positive results, others mainly negative. And then so the label distribution, feature distribution, and the quantity of data differs between different institutions. So when this happens, you see that the global model trained across different clients tend to perform poorly compared to centralized case or the ID case. You see scenarios like slower conversions, you have biased updates, or large performance gap between different clients. So essentially, the model could become pretty unfair, where it's good on one of the clients, bad on the other clients. And and then the research objective mainly is to uh, kind of look into the existing gap of federated learning research. When we look at federated learning aggregation algorithm like FedAverage, FedProx, they have been only evaluated on toy data sets like MNIST, which are like artificially created partitions. So which makes it unclear how these different aggregation algorithms perform real life non-IDness. So the central question is how could the existing aggregation strategies perform under the realistic non-ID molecular data and how we can systematically benchmark them. And we see on the figure, we this is a simple figure of how federated learning performs its overall pipeline. So the project aims are kind of four-folded. First one is to build the StratoFL, which is a molecular benchmarking frameworks containing different data sets, featureizers, partitioners, models, different strategies. By here, I mean aggregation strategies, and even differential privacy. And then second, to design those realistic non-ID partitioners and to evaluate uh, aggregation strategies across these non-ID settings. I think one of the partitioners was also like already contributed to Flower, so you can actually access this from Flower's code. Uh, and then I wish to provide a reproducible evaluation on two molecular tasks, mainly aqueous solubility as well as multi-assay activity classifications. And as an extension, I've integrated DP uh, and to assess the privacy utility trade-offs between different aggregation algorithms. Oops, next slide. So here's a high-level diagram of the framework. On the left, I would say every everything starts from a YAML configuration files, which defines every component of an experiment, which datasets are we using, which feasorizer are we using, partitioners are we using, and so on, which makes the kind of experiments very reproducible. And then each configuration loads in the molecular uh, modular pipeline, which consists of five different key modules. You have data adapter that reads and pre-processes the data sets. And then we have featureizers, which I'm going to introduce in the later slides. We have partitioners that distribute data across different simulated clients. And we have the model aggregation strategy that defines the local training and aggregations. And finally, we have this optional differential privacy wrappers. Okay. So next up, I focus my project mainly on two sets of data sets. The first is aqueous solubility, which contains around 16K different molecules. They're all extracted from ChemBio, which is a large bioactivity database that's being widely used in drug discovery space. And then the second data set is what I call multi-assay activity. It's a much larger data sets with around 430 K molecules across 281 different tasks. And then you see the density is about 3%, which means a lot of the molecule task pairs are missing, which kind of reflects the true nature of bioassay data, which is highly sparse and incomplete and being distributed across different laboratories. Next up, we have featureizations. So once we have the data, next up is to extract feature from the data. So I think when we consider molecular machine learning, the difference between molecular machine learning and let's say traditional machine learning is that for traditional other set of machine learning, you have data sets already popularized with the feature. But most of the time when you're doing predictions on molecules, you actually featureize yourself because each molecules can be represented by this unique representation called Smiles representation that uniquely defines a molecule, saying, okay, what are the atoms in this molecules? What are the bonds in this molecules? So featureization basically converts this information we have into some fixed length vectored for training, for tabular data, for feed-forward neural network, for example. Um, So for tabular representations, each molecules can be encoded into three different types of feature. You have descriptors, which are some physiochemical properties of the compounds, such as molecular weight, um, log P, topological polar surface area, which is kind of specific to the field, and you have fingerprint, which are binary vectors, also like kind of how specific to the field, how you featureize the data, and etc. So the resulting feature vectors will be fed into, let's say, in this scenario, a simple feed-forward neural network. And then we could see the visualizations here, how you transfer from the smile string to the feature vectors you have, and then feed into the model to get the predictions. A different form of featureization, which is kind of more interesting here, is what we have for the graph representation when we're using a graph neural network or message passing neural networks. Uh, the incentive here of using graph neural network is because we can think of each molecule as a graph with atoms as the node and bonds edge as the edge of the graph. Therefore, we could incorporate the graph neural network to do predictions of of molecular properties like aqueous solubility in this case. And we can see it from the graph that shows an example of the featureizations we have. Uh, on the left, bottom left, we see a molecules, and then we have highlighted one of the atoms and one of the bonds and how we featureize them. Yeah. So this is the graph representation featureizations. So after featureizations, let's move on to non-ID that I briefly covered. Uh, so we need to define like what kind of non-IDness are there. This table kind of summarizes five main types of non-IDness and federated learning. We have feature distribution skew, where we have each client's input space differs, but the mapping from features to labels being consistent. Similarly, we have label distribution skew, where we have some clients seeing, I would say, the label proportion vary across different clients. Or in the case of accurate solubility predictions, you might see uh, one of the node having labels that's consistently centralized in a specific range. Um, and you have same label, different features, same feature, different labels, and you have quantity skews. So here's the non-ID taxonomy. And then real-world federated learning usually involves multiple of these simultaneously. So in this project, I implemented partitioners targeting each of these types so that we can systematically explore their effect on the effect of non-IDness on the performance degradation, let's say. So in total, StratoFL introduced five main partitioners. We have the continuous partitioners, scaffold clustering, multitask pathological, multitask class ratio, and multitask Dirichlet partitioner. Collectively, these could cover the feature skew, label skew, and quantity skew, which I would say the diversity allows controlled, reproducible experiments on non-IDness. Due to time, I'm going to cover the two main partitioners, the continuous and scaffold clustering here. So the continuous partitioner is, I would say, the simplest partitioner, but also very general. So it introduced the skew by sorting the molecules according to a continuous property, let's say molecular weight or solubility, and then assign continuous segment to different clients. And then the degree of non-IDness is being controlled by this parameter called strictness, which linearly blends the true property values with Gaussian noise. When strictness equals 0, we get IID split, which can be seen from the bottom left graph here. We have five different clients. Each of their distribution are pretty not IID. And then when you gradually increase the strictness, you can see increased non-IIDness being introduced. And then at the very end, when strictness equals 1.0, you see all the clients have very, very different distributions in terms when we think of this property. So that's the continuous partitioner. We also have scaffold clustering partitioners, which kind of uses this property of chemistry scaffold, which is the core structure of a molecules, and then do some steps of extracting the scaffold, computing the fingerprint, doing some PCA hierarchical uh, clustering, and then mapping different clusters to clients. So here are two example partitioners for the projects. And then next up, we have different aggregation strategies. So how do we combine updates to from these diverse clients? We use Fed average as the baseline, which simply average the model weights and weighted by dataset size. I've also experimented with FedProx, which adds the proximal term in the loss to keep local model close to global ones. I've also experimented with FedNova, Scaffold, and Flit. And this slide kind of gives an implementation overview of uh, kind of having these different strategies in a unified framework. And then at the very end, I kind of summarize what are the main components and what are the actual components I need to implement for these specific strategies. Yep. And then this figure shows how these different strategies integrate within the Flower framework. Flower separates concerns into three layers. We have client, server, and strategies. So each aggregation method will plug in at the appropriate layer. For example, I could define a custom optimizer on the client or a new aggregation rule on the server. And then, yeah, this is basically the Flower architecture. And then some specific to the strategies I've implemented. Next up, we do the evaluation overview. So the evaluations aims to answer four core questions. Firstly, how much of the performance degrade when data becomes non-ID? Secondly, to look at which aggregation strategies can mitigate the degradations. Thirdly, to see how they scale across different clients counts and local training regimes, doing some cross-scenario evaluation. And at the end, I'd have this integration of differential privacy to explore the privacy utility trade-off uh, using compare different aggregation algorithms. Here's a simplified table that shows the performance degradations under Fed average. Uh, we can see in the regression task, if we consider the baseline, the centralized and ID case, they performed pretty similarly. But once we introduce label skew and feature skew, we see degradation in performance. And then we see similar case in the classification tasks using different partitioners. Okay. So next up, as I said, I want to objectively measure how heterogeneous each partitioner is. So I compute several statistical metrics to measure, okay, for example, the Wasser stain distance measures the overall shift in the distribution between clients. I've used KL divergence as well, and then as well as the KS test, which gives us a p-value to indicate whether two distribution differ significantly. Yep. And then here's a visual counterpart to what we have on the last slides, for example. On panel A, we see kind of what kind of non-IVness is being introduced when we use a continuous partitioner with strictness of 0.5. And then and the number B is how we introduce feature skew and quantity skew when we do the scaffold clustering. And the third one is kind of the PCA visualization in 2D of what if we use uh, continuous partitioner bimolecular weight, then in the feature space, how would different clients being seen differently, which is pretty interesting here. And then, so with the non-IDness being quantified, the next step is to test out how different algorithm performs. Uh, and I'll have this table on the next slide, which, so in my dissertation, I've documented in detail like how each performed, but since this is a presentation, I'm gonna this is a summary across different partition tasks. We see for regression tasks, scaffold dominates in most feature skew cases, and then FetNova Flit also performed decently. For the multi-asset classification task, FetNova and scaffold alternate as the top performers depending on the class ratio, for example. And then this is this concludes the part to compare how different aggregation algorithms can help mitigate the non-ID-ness. Next up is to look at factors besides other than just pure, let's say, performance accuracy, but other issues, for example, the convergence and stability, which kind of illustrates different convergence behavior when I use different uh, aggregation strategies. On the left, we have the feature skew being created here. On the right, we have the label skew being created here. And we could compare to see, okay, how fast are different uh, aggregation algorithms making this convergence be, and how stable are they? Another thing I compared is how these algorithms scale as the number of clients increase. I've tested from 10 clients to 20 clients to 40 clients, which I think as expected, we see the performance generally decline as stable as data become more fragmented. And then in this case, scaffold maintains as the highest R square value and exhibit the least degradations. And then another one is fairness, which is pretty interesting. So does every client benefit equally? So here I assess per client performance distributions over the final 20 rounds of the training, which means um, if I look back, if I look back on the training process and I evaluate the global model on, let's say, the each of the clients' data, how does the performance differs across different clients? I mean, in the ideal scenario, we want to train a global model that's equally good for every client. So every client can apply this model to their own data sets, and it's being better than they training only on their local models. And then I think if we consider fairness under different non-ID scenarios and ID scenarios, we see scaffold performing better than Fed average. And then as the last step of the evaluations, I evaluated the how differential privacy interacts with these aggregation algorithms. Actually, thanks to Mohammed, actually, when I was doing the project, I've asked several questions to Mohammed, and he was able to help me. So here we applied a server-side DP using adaptive clipping and Gaussian noise, and then to test different uh, privacy budgets. Lower budget absolute means stronger privacy with no noise. And as expected, we see all models degrade with stricter privacy, but I would say the degrees varies. I would say if we can see across all different practitioners, the scaffold feature skew and continuous label skew, the scaffold algorithm consistently achieve the highest utility. In this case, is the lowest loss, and then that's kind of the conclusion for the uh, privacy utility trade-off section. I've also, to verify these differences, aren't just like random verifications, done some statistical tests showing uh, comparing this distribution of results across different algorithms. Okay. And then kind of to conclude, here are the lesson learned for the projects. First, the conclusion, there's no one-size-fits-all algorithms. So each strategy has its strength for specific data regimes. For example, when we consider extreme imbalance, FatProx might be more superior. FatNova was also superior when we consider moderate skew and scaffold for feature-driven non-IDness. Secondly, I would say the way we split the data matters enormously. Artificial ID partitions can give misleading conclusions, and then chemistry meaningful partitions like the scaffold partitioners I introduced in the property-based splits, they reveal behaviors invisible in the standard benchmark, like historical papers. And then thirdly, the result is scaffold consistently preserve the best performance under the differential privacy scenario. And finally, we need a standardized, reproducible FL evaluation pipeline to enable fair cross-algorithm comparisons and community benchmark, which is the Strato FL framework I introduced. So yep, that's concludes my presentation. Thank you, everyone.
Yeah, wonderful. Very complete piece of work, this one. Very interesting. Um, let's just see if we've got any questions. But anyone on the call, feel free if you want to ask questions, just go for it, really. There's this one from Slack saying most FL is done on things like Sapphire 10. What did you discover about using this kind of data that was different?
Sorry, could you repeat the question?
The person's asking, they're making a connection to the fact that most of the results out there are based on data sets like Sapphire 10. I guess data sets of that kind, whereas this data set is quite different. Um, so because of that difference, what did you kind of observe? I know you had lessons learned slide, but like what were some things that jumped out to you about how FL is different under this type of data?
Hmm, good question actually. I think under when we see those kind of historical uh experiments with those standardized data sets,
Mm,
I would say those does not match the realistic scenario. And when I do test on realistic scenarios, I would say uh, my lesson learned is that because I think if we consider a lot of other research into the field, they might easily conclude that okay, this aggregation algorithm is the one that's superior under a
mm-hmm,
specific scenario. But I think what I realized after running this experiment is that I would say it's more application specific. And then there's so many different types of non-ID scenarios that you can think of that could appear in the real life settings. So
mm,
I would say in the actual world when we are actually kind of implementing stuff and actually using uh, the federated learning, and we it's better that we consider all sorts of different aggregation algorithms, and we might find one that's kind of most suitable for this specific setting.
okay, cool. I guess conventional wisdom is things like FedProx does pretty well under non-IDness, and FedAverage does, generally pretty well on many settings. Like it's a pretty sometimes even a hard baseline to beat, depending on how you evaluate. So I guess you're saying that there's no consistency though. You kind of maybe would you
Yeah.
say that kind of consistency that people might have as an intuition is a bit wrong? That
I
like
wouldn't
it
say
really
it's
you
wrong,
really
actually. Actually, the thing you just mentioned, I think it's correct. I think,
that's
which is
correct.
also consistent with my experiments. I think under non-ID settings,
Yeah.
Fed procs almost always better than Fed average, in my case. So
Yep,
I think,
makes sense. Yeah, I wasn't really saying that I wasn't saying that necessarily is wrong, but I think it's worth verifying
yeah,
because a lot of the data that people do experiments on is pretty far removed from the data that people are actually motivated to do FL in. So
yeah.
it's interesting. Cool. Let me see what else I can find. This is a simple question. They're asking for this data set, does that correspond well to tasks done in the domain?
I see. So when I was thinking about the actual data sets, I was kind of
Mm,
doing some literature review of stuff or tasks commonly being done in the domain. So I chose these two tasks because I would say these does correspond pretty well to
mm,
kind of two of the most frequent like research directions or prediction directions. And then and then the fact I've used CanBL, which is a website that collects data set from all different like scientific journals, which kind of actually mimics the real world non-IDness because the data sets on its own, I collected them from different places as well, and then kind of merged them together. So I think it's fairly realistic. Yeah.
yeah, it's a pretty good job. Great, cool. I don't see anything. Well, those are two good questions I found. So yeah, good stuff.